Okay, so congratulations, Javier. I apologize for the beginning of the course, or perhaps for half of the course, as it will be an extended version of Omegar's lectures yesterday. So I'm going to talk about foliations of Codimension 1 on projective spaces. And the plan of the lectures is essentially the following. So today, I want to talk about definitions and examples. Tomorrow, I'm going to say something about stability in the sense of that Omegar discussed yesterday. As he already done some of the job, perhaps these two lectures will be merged in, I will use some of the space that Omegar gave me here to expand the third lecture, and it will be about classification. Where we are going to, for instance, sketch the proof of this classification of foliations of degree 2 that Omegar mentioned yesterday. And in the fourth lecture, I'm going to talk about structure. Mainly, I will try to extend the results that we know on degree 3 to on degree 2 to degree 3 and higher degrees. Of course, we are not going to give a complete answer, but we'll try to outline a possible approach to attack this problem. So please apologize me if I'm starting with some very basic stuff, but I'm aiming this lecture to students. So I will start by defining a smooth foliation on a complex manifold. So I'm considering X a complex manifold. And most of the time, I'm going to restrict to the category of projective manifolds, which are submanifolds of projective space. And foliation on X can be defined in a number of ways. Perhaps the simplest is by giving an open covering and on each open set of the covering, a submersion where Q is the codimension and so at the open set UI, we can look at the level sets of these submersions. And we can compare these level sets with the level sets of submersions of another submersion on intersecting open subsets. And we impose that this collection of submersions is coherent in the sense that the level sets coincide, and this is the same thing as saying that I have some local diffeomorphism from the images So when I think of a foliation, I essentially have this picture in my mind. And from this picture, we can, from this setup, we can define some, we can attach some objects to this foliation, and perhaps the most, there are two that are very important, which are TF, the tangent bundle, which is the subbundle of the tangent bundle of X formed by vectors tangent to the levels of the submersion. So these submersions can be analytically continued to form the leaves of the foliation. And these are, the tangent bundle is the tangent space, the collection of tangent spaces of these leaves. So this is a holomorphic subbundle of Tx. Another distinguished object that we can attach to foliations is the cotangent bundle. And it's a subbundle of the conormal, of the cotangent bundle of the, sorry, conormal bundle, which is a subbundle of the cotangent bundle of the manifold, and its local sections are one forms vanishing along the leaves of the foliation. So if we are really willing to study these objects on projective manifolds, we have to be more, let's say, we have to allow more. These objects, these conditions are too restrictive. For instance, there are small foliations on compact complex surface are classified. There are not so many of them. Well, essentially classified, and there are still missing details, but we have a pretty clear picture of what is happening. And the situation should be more or less the same. The picture should repeat for codimensional foliations on compact complex manifold, although this is not yet settled. Anyhow, there are, even if there are, if we go for higher codimensions, there are very natural classes of examples of these objects that deserve to be studied. For instance, if we start with X, an holomorphic symplectic manifold, and we take H, a hypersurface, then the restriction, let's put here 2n minus 1. The restriction of the nth minus 1 power of the symplectic form to H defines a smooth foliation. Of dimension 1, which is still mysterious. So there are many smooth foliations, at least there are as many as hypersurface in holomorphic symplectic manifolds. But if we look for, if we fix the variety, for instance, if we look at projective spaces, there are no objects of such kind except perhaps for foliations of codimension 0 and codimension n. So in the case of codimension 0 is the foliation with only one leaf. And it's the foliation here where the leaves are points. So anyhow, to study foliation with one leaf is already a very important subject. It's complex geometry. Study foliations by point is as important, but it seems that we should have something in between. So we have to try to extend this definition to include singular foliations. One natural choice would be just to try to, instead of looking at submersions, look at open maps or things that are generically submersion, but this is still too restrictive. Projective space don't carry these objects. So a good viewpoint is try to, instead, to generalize this viewpoint. So instead of starting with tangent subbundle, we start with a singular foliation. Instead of starting with smooth, instead we start with a subbundle, we start with subsheaf of the tangent sheaf. I will denote by the same letter the tangent sheaf and the tangent bundle, but we start with a subsheaf, which is involutive, meaning that if I take two local sections, then its bracket is still a local section. And without apparent singularities. The point is that if you are willing to work in this level of generality, we can do silly stuff. We can just take a subsheaf and we can tensor it by an ideal sheaf, creating some singularity. So the technical condition is that the co-kernel of the inclusion is torsion-free. Okay? So for those that are not used to this language of sheaf, this might seem a little bit harsh. But there is another equivalent definition, which is more concrete and very close to the original picture, which is the following. We can just take a foliation as a pair is a pair F sing F, let's call F dot, where F dot is a smooth foliation on X minus sing F, and sing F, the singular set of F, is a closed subset, analytic or algebraic subset. And to be plus a maximality condition that I'm not going to unravel, but which essentially says that I do not have some analytic subset smaller in such a way that this foliation extends to the biggest open set defined by its complement. Again, this is the history of talking about apparent singularities, as we do for one variable functions, right? But of course, a function that's a regular on point, we can just say, well, this now is a singularity, and we can remove the singularity. Here's the same thing. I'm supposing that maximality condition that I cannot remove n. Well, it depends on the offset or the, well, extremality condition. Oh, thank you. Okay. Very. Sure. Yeah. Let's also impose codimension. Right. Codimension of singular set of F. At least two, because indeed, as Mark is pointing out, the equivalent between two definitions, behind the equivalent, there is a Hartog's phenomenon where we can extend the things defined on the complement to the whole variety. And to do that, we have to impose that the codimension is sufficiently big. So for me, 2 is big. So these are the objects. And in the case of codimension 1, the things are considerably simpler because the inclusion, so let's specialize to codimension 1. The inclusion of this tangent subsheaf on Tx can be always realized as the kernel of a morphism to a line bundle. So in other words, I can always write F as where omega is a one form defined with defined by one form with coefficients in a line bundle. So again, if you're not used with this terminology, you can always put it very concretely. It's just that I have a covering on each open set of the covering. One form satisfying these conditions that they patch together by a non-vanishing holomorphic functions. So in some sense, the codimension 1 foliations are like hypersurface, as they can be defined by only one equation. Of course, here, I have not written anything about the involutivity, and I have to impose it through the Frobenius condition, right? So these are the objects we are going to study. We are going to study one form with coefficients in line bundles on the projective space. As we are going to see in a moment, these are very concrete objects that can be described by only one polynomial equation. But before doing that, I would like to present some examples of foliations, in particular examples of codimension 1 foliations. So, any questions so far? So, perhaps the simplest examples are foliations by algebraic leaves. So, in this setup, we take see an algebraic curve or a compact complex manifold of dimension 1 or projective curve. These are projective curves. And F, a meromorphic map. Then the level sets of this map will define a decomposition of the variety, which can be seen to be a foliation. Suppose that this should be more or less clear. The dots in the definition of F is perhaps due to the existence of indeterminacy points, which contain infinite numbers of level sets, of closures of level sets of F. And this can be easily seen to define foliation in the sense that we discussed. If you want, this can be seen, this can be an exercise to prove that this gives rise to a foliation with leaves equal to the level sets of F. And here there is something, one has to be a little bit careful with this kind of definition because, of course, if we are going to give you two different functions, two different meromorphic functions, we should be able to compare the foliations that they define. And a first thought would be to say that, well, there is a bijection between level sets, but it's not true because we are not supposing here that the level sets are irreducible or anything. And, but the things are not so bad because one basic result that we can use from algebraic geometry or complex geometry is the Stein factorization theorem, versions of which already appeared in the work of Poincaré on the Poincaré problem, which says that, well, if I start with this object, then there exists another curve, let's say C tilde, and here a finite map from C tilde to C, such that, and another meromorphic map G, such that G has irreducible generic fiber. So not only rational maps define foliation, but we can always find a rational map which gives a pretty good description, which level sets corresponds to leaves. Also, there is the question of characterizing when a foliation is a foliation by algebraic leaves. And there is this theorem by Joannoulou, which after has been extended by Etienne, which says that codimension 1 foliation on a compact complex manifold is defined by a meromorphic map if and only if F admits infinitely many compact invariant hypersurface. Okay, so here we have this, I have to define what I mean by invariant hypersurface. I'm going to say that a compact complex hypersurface is invariant by the foliation if, when restricted to the complement of the singular set, is a leaf of the corresponding smooth foliation. Right? It may contain, this compact hypersurface may contain singularities, as here. Which manifold? My manifold are connected. Manifold is connected, smooth and connected. Okay, and the next class of examples that I would like to discuss can be seen as a natural generalization of this one. And these are the foliations defined by closed Dolan forms. Closed meromorphic one forms. So, well, this is it if you want. If I have a closed meromorphic one form, I can look at the kernel of it, can define a foliation. And these previous examples are, of course, also defined by a closed meromorphic one form, because as soon as I have a map, I can take a closed meromorphic one form on C that we know that exists, and pull them back with F to produce a closed meromorphic one form on X, which will define the foliation, the same foliation as F. But if I restrict myself if I restrict myself to the compact Kähler manifolds, then we understand, we have a clear picture of what these objects are, and we can, for instance, look at two things. So you have these poles, which can be written as a part of logarithmic poles, with non-logarithmic poles. Again, big enough to higher order poles. Big enough poles, it means order at least 2. Giving evidence that 2 is really big. And this part, logarithmic poles, comes, as we all know, with a residue. So here I have we have the logarithmic part, which will be a divisor, lambda I di. And the classical residue theorem can be generalized to show that the real term class of this divisor is 0. And reciprocally, it's an exercise for those that knows the terms defined, that when we have a C divisor, so this is an element of H2xc, given a C divisor with 0 complex Chern class, then we can define a logarithmic one form with the residues. Of course, this correspondence is not unique. There is some ambiguity, and this ambiguity comes from the existence of holomorphic one forms. So we can now take out this logarithmic part, choosing correctly the holomorphic part to avoid residues, and what remains is something with high order poles, and we have this decomposition of holomorphic one forms that can be traced back to the beginning of the 20th, end of the 19th century. And anyway, just to say that we can... Sorry?
I don't understand the composition of poles.
You look at all the poles that are simple. These are logarithmic and have a residue attached.
If take dz over z plus z squared.
You want this?
No.
This? This? You are kidding. You want me to do continued fraction here right now? No. Oh. This. But the point is that we can write this as... What I'm saying is that I can write this as something of higher order poles, and since P1 is simply connected, this will be a differential of a meromorphic function, probably a polynomial. But
Zero is a logarithmic pole or?
0 is a logarithmic pole, of course. Pole of order 1, and it has a residue attached. These are different from 0. Okay? It's the first lecture. We are warming up. Okay? So, the third class of examples are...
What is the conclusion there for foliations right close?
The conclusion is that we have these objects, which are somehow structured and have a clear structure in the Keller case, and we can also produce examples of these by taking divisors with zero-term classes. Because the point, again, is that here we are in a situation that was fairly simple to produce examples as soon as we are in the algebraic world. Here again, we are in the same situation, because if you are in the projective case, we have a lot of divisors, and we can manage to conclude these. So, as in the lecture of omega, we also have foliations defined by actions. So if I have G, a complex Lie group, and an action of holomorphic action of this complex Lie group on X with codimension 1 generic orbit, then we have a foliation defined by G, by the action of phi, the action of G by phi. And here, I would just like to mention that a natural question is, are we getting something new? Are we getting examples that do not fit in the previous two classes? And the point is that no, from just this rough description, there is nothing new. And the reason is very simple. It's just that we have to analyze two cases. The first case is that the generic orbit is here you have to put a hypothesis, X scalar, or projective if you want. Suppose that the generic orbit is algebraic. I'm abusing the language here. In the Keller case, this means that it's an open set of a compact complex hypersurface. Let's call this algebraic, even if we're in the non-algebraic world. Here we can use the Joannou-Logis theorem to prove that these are defined by algebraic leaves. or the generic orbit is not algebraic. But this means that the action, this means the following, the action defines a Lie subalgebra of the Lie algebra of the automorphism groups of X. Or in other words, let's say, it defines a map from G to the automorphism group of X, even to the irreducible component of the identity, which induces a map on Lie algebras. This is known to be under this hypothesis, to be a Lie group, finite dimensional Lie group. And we can look for the closure. If this, well, two things, this group is a Lie group, and the action, the closed subgroups, the image of closed subgroups here are algebraic subvariates in the sense that I just described. And so when you have that G or phi, well, and G bar, the closure of G in out X is different from G, then we can produce either G bar has generic orbit algebraic, and we are done, or we can produce a V in the Lie algebra of G bar, but which is not on the Lie algebra of G, which is a symmetry of the foliation F, foliation induced by the action. And very, very old computation, essentially due to Lie, shows that F is defined if omega is a meromorphic one form defining F, then omega divided by the interior product of omega and this infinitesimal symmetry is closed. So again, we are in the previous situation, in the previous case. So another procedure that we can do, that we can use to produce new examples of foliations from the examples that we already know, is taking quotients. So we can talk about quotients by finite groups. Take foliation in the previous two classes and look at this. And there is one very interesting example due to Lins-Neto of this thing, that when we start with foliation, well, we start with this distinguished elliptic curve, the one that has an automorphism of order 6. We look at a certain element in the automorphism group of E of order 6 and consider the action of phi square, the diagonal action of phi square on the surface and can be shown that this is bimeromorphically or birationally equivalent to P2. It's again a nice exercise, computation of Euler numbers, characterization of projective spaces, projective planes. And this automorphism has the peculiarity that it preserves, let's call this phi. If omega is holomorphic one form on this torus, which will be something like lambda dx plus mu dy, then can be seen that phi star omega, as is the diagonal action acting, will be some constant times lambda dx plus mu dy. And in this case, we see this constant is different from 1. It will be a root of the unity of all the three, if I remember correctly. And this equation says that although the one form do not descend to P2 or to a rational surface, the foliation will do, because these two forms define the same foliation, and is a foliation which is not in the previous two classes for a generic choice of lambda and mu. Of course, this nu here has to be taken with a grain of salt, because it's nu only for in the context of this talk, because it is a particular case of the next class of examples that I want to discuss, which are the transversally projective foliations. So here, again, this is a complexification of a classical construction, of a classical class of examples on real foliation series. And it goes as follows. We start with a representation of the fundamental group of my manifold to the automorphism of P1. And then we can, using these automorphisms, we can construct a P1 bundle over X carrying a flat structure, carrying what we like to call a horizontal foliation by this classical construction that goes as follows. You take the universal covering, on the universal covering, we consider the foliations defined by this submersion. These are just what I'm calling the horizontal leaves. And I make P1 X act on the product first as deck transformations on X tilde and through rho on P1 to produce Y, which will be, so the quotient, take the quotient, obtain Y, which will be a P1 bundle carrying codimension 1 foliation transverse to fibers. So this is a new example. If this representation is sufficiently complicated, then this will be an example of a foliation, or codimension 1 foliation that is not on the previous two classes. And we can also take another variation we can take now. We have this Y going to X, and I can now take a meromorphic section. let's say here I come with a foliation, a horizontal foliation H, and we can define F foliation on sigma as the pullback of H. We have just to ensure that the graph or the image of this section is not an invariant algebraic, not invariant algebraic subvariety, and then we can do this construction just by pulling back one form to define the foliation on Y, this horizontal foliation on Y. And there is also a version of this construction with boundaries. Or if you want, let's call it logarithmic version. Where now you will start with a complex manifold and a divisor. We take a representation of the complement, do this construction on the complement, obtain a foliation like this on an open manifold, and we glue models in the boundaries to compactify everything. So this, at the end, will give the following. We'll give Y, a P1 bundle over X, and now H, the horizontal foliation, will be no longer everywhere transversal to the fibration as here, but will be transverse to the generic fiber. And the pullback of H by this is what we call a singular transversally projective foliation. Okay, so these are really new examples. And there is still one last class of examples. It goes until 1020 or 1030? 1030. Okay, there is still one last class of examples that I would like to discuss, which again, generically do not fit in any of the previous ones, which are examples that have already been discussed as soon as there's understanding in previous talks, which are foliations on surface. So far, the constructions that I've presented do work on surface, can be used to construct examples of foliations on surface, but it happens that on the case of projective surface, the world is much larger than this, is much wilder than this, and much more mysterious than this. For instance, we know that let's make an algebraic version of the algebraic counterpart of the lecture, of results presented in the lecture of Ilyashenko yesterday, which is again the theorem of Bernoulli, which says that a generic foliation on P2 does not admit any invariant algebraic curve. And now it's 6, right? Of course, with all the previous constructions can be used to produce another examples by taking pullbacks by rational maps to produce examples on higher dimensional manifolds. And this will give rise, the pullback by a rational map of this thing on P2 will give rise to foliations on P3 or on any other projective manifolds, as they all can be mapped to P2, which are not in the previous class. Because one thing that can be shown is that it's more or less clear that in the all first examples, foliations defined by rational maps do have invariant algebraic curves. Foliations defined by closed one forms do have algebraic curve on P2 because P2 has no holomorphic forms. And essentially to the same reason, foliations, the transversely projective foliations on P2 will have invariant algebraic curves. So these are really new classes of foliation, and it's the generic class, the generic example, which do not fit in the previous picture. Okay? As I have not proved anything, let me give an idea of a proof of John Lewis' theorem, which is not his original proof, but somehow tell us how the general methods of algebraic geometry can be used to study foliations. So first we have to understand what is a foliation, have to equate what is a foliation on P2. Let's just recall from Omega's lecture that these are foliation on P2 of degree D. So let's say we have a degree, which is the number of tangencies with a general line, a generic line. So if we think the foliation as defined by one form with coefficients in some line bundle, we know that they are all, the line bundles on P2 are indexed by integers. Then the tangents of these can be seen as follows. We look for the inclusion of a line to P2, the linear inclusion. We pull back this one form to obtain one form on P1 with coefficients in the line bundle OP1K. But then this, as a line bundle, is nothing more than OP1, omega 1 P1 is O minus 2, so this is OK minus 2. And now I'm looking to the zero of this, and the cardinality is just the degree of this guy, which is K minus 2. In other words, a foliation is defined by a section in K equals B plus 2. And this can be seen as using Euler's sequence as a collection of polynomials, d plus 1, dx plus b, d plus 1, dy plus c, d plus 1, dz, subjected to the Euler's condition 0. As Omega explained yesterday, the integrability condition in dimension 2 plays no role. Now, an algebraic curve, as we all know, is defined by H, a homogeneous polynomial. And it will be invariant by F, by omega, by the foliation defined by omega, if and only if d omega is equal to H over theta for some polynomial to form. So it's certainly an algebraic equation involving a foliation, or one form in omega 2, a polynomial of degree, a fixed degree, and a two form that will have degree d, the coefficients will have degree d. And this equation certainly defines an algebraic subset let's say of degree L. let's say here, two forms with degree D. And this condition certainly defines a closed subset here, which, by one of the many versions of quantifier elimination, can be seen to induce a closed subset here, or in even here. So, in other words, the projection of this set by a proper map is an algebraic set. So we'll define here. So here I have the set which parameterize the pairs foliation and invariant hypersurface by the corresponding foliation. And I can even go one step further and say that you see that I have this, or let's start calling this folding. Okay? And then as we are going to say something about the generic foliation, all that we have to prove is that this set ZD, the union, that each one of these sets ZDs, which says that, which parameterize the foliations of degree D that leaves, ZL. Foliations of degree D that has an invariant algebraic curve of degree L, invariant. We have only to show that the ZL is different from for D for every L, because the union of algebraic subsets of an algebraic variety can never spread the whole algebraic variety unless one of them is equal. So the point of these results is that it suffices to produce one example. And that's what João Lu did. He did this argument essentially in one page, and then takes 20 or 30 pages to prove that a given example has this property. So I have 2 minutes to give an idea of how we can manage to prove this kind of statement without producing examples. And the idea is very simple. It will be just a sketch. I look here at Fol D, and I look here at P2. Right? So the first thing that we look at is the singular set of the foliations and how they vary. So for a generic foliation, I will have a finite number of singularities. And here I also have this one forms on the boundary that has codimension and irreducible set, but it's not really a big deal. And the point is that this will draw, this singular set, let's say a universal singular set, will draw an algebraic subvariety of this product. Of course, there will be some confluences. The things will be some kind of, if you look to this projection, the things seems to vary very wildly. But if you instead look here, and remember that every point on P2 is like any other, you promptly realize that in this direction, this projection is very simple. This gives a projective bundle over P2. And in particular, shows that the singular set that in this direction seems complicated is a smooth variety, which is a bundle over P2. And then, just looking at basic properties of intersection of analytic subsets, we see that the ZL intersect, if ZL is equal to the space of foliations, when we intersect it with the singular set, knowing that every invariant algebraic curve has at least one singularity, by Gómez-Mont, Cziad-Verjovski's theorem of Camacho-Side's theorem, as you want, you deduce that through every singularity of every foliation, there exists an invariant algebraic curve passing through. And we are almost done, because then it's essentially a much simpler problem. Instead of producing a foliation which has no algebraic leaves, we have just to produce an example of one foliation with one singularity without algebraic separatrix. And this can be done very easily. It can be done, for instance, with foliation defined by closed meromorphic one-forms. To do that, we have to ask that the degree is at least d plus 2. D must be at least 2. So it's just to give an idea that usual methods of algebraic geometry allow us to revisit and sometimes even improve results from foliation theory. So that's the punchline here. And just to end, let me say that today, we do not know, so this shows that this class of examples is really new, well, new in the sense of this talk. And also, let me just say that today, we do not know any other example of codimensional foliation on projective manifolds. Every foliation constructed so far on projective manifolds can be recovered by a combination of these examples. Transversally projective plus pullback, or so on. So in some sense, we have today we have this dichotomy. Either the foliation is transversally projective, because transversally projective involves all the previous examples, or it comes from an algebraic surface, on a foliation on a projective surface by means of a pullback. We don't know anything else so far. Okay. So I finish here.
The definition you gave of singular foliation. So outside of the singular set, I guess you have the partition into codimension one submanifolds. What happens on the singular set? Do you have some sort of partition there too?
It's not like in Poisson geometry, no. It's not very clear what kind of partition we get. There are works trying to stratify the singular set according to the rank of the tangent sheaf. But the things are not as clear as in, for instance, Poisson geometry.
So at the end of your talk, you said that you don't know examples of codimensional foliations on algebraic varieties which are not of this family. Why did you use the word algebraic? I mean, do you know examples of non-algebraic varieties?
I like to use algebraic now and then. No, I don't know. I also don't know.
You don't know?
No. I even think that there are even positive results for non-algebraic varieties with the pseudo-parallelizable, blah, 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 saying that they do fit in this picture. But again, the point...
You said that we don't know, but maybe you know. We don't know. He knows.
No, I don't know. I don't know. If I knew, the course would be different.